Have you ever wondered how your phone can pinpoint your location within a few meters anywhere on Earth? Whether navigating city streets or tracking a delivery, the global positioning system seems almost effortless. Yet behind that simplicity lies one of the most profound ideas in physics. Without relativity, GPS would fail in minutes. The system that guides billions of devices every day depends on subtle distortions of space and time. Welcome to Mattermosaic, piecing together the universe, one discovery at a time. Today we explore how GPS works, why time itself runs differently in orbit, and how Einstein's theories of relativity quietly power modern navigation. The Global Positioning System, commonly called GPS, is a network of satellites orbiting Earth. At any moment, at least 24 satellites circle the planet, each carrying extremely precise atomic clocks. These satellites continuously broadcast signals containing the exact time the signal was sent and the satellite's position in orbit. Your GPS receiver, such as a smartphone, picks up signals from multiple satellites. By calculating how long each signal took to arrive, it determines the distance to each satellite. With distance measurements from at least 4 satellites, the receiver can compute its exact position in 3-dimensional space using trilateration. At first glance, this sounds straightforward. Measure time, convert it to distance using the speed of light, and solve geometry. But here is the complication. The clocks on the satellites do not tick at the same rate as clocks on Earth's surface. This discrepancy arises from relativity, developed by Albert Einstein in the early 20th century. Relativity consists of 2 key parts: special relativity and general relativity. Both affect GPS in measurable ways. Special relativity deals with motion. It predicts that clocks moving relative to an observer tick more slowly than stationary clocks. GPS satellites orbit Earth at about 14,000 kilometers per hour. Because of this high speed, special relativity predicts that their onboard clocks should run slightly slower than identical clocks on Earth. General relativity, on the other hand, deals with gravity. It predicts that clocks in weaker gravitational fields tick faster than clocks in stronger gravitational fields. GPS satellites orbit about 20,200 kilometers above Earth's surface, where gravity is weaker than on the ground. According to general relativity, their clocks should run faster than ground-based clocks. These 2 effects work in opposite directions. Special relativity slows the satellite clocks, while general relativity speeds them up. When scientists calculate both contributions, the net result is that satellite clocks run about 38 microseconds faster per day than clocks on Earth. That difference may seem tiny, but GPS requires extraordinary precision. Light travels about 300 meters in 1 microsecond. An error of 38 microseconds per day would accumulate rapidly, causing navigation errors of several kilometers within a single day. Engineers therefore incorporate relativistic corrections directly into the GPS system. Satellite clocks are adjusted before launch so that, once in orbit, their tick rate matches Earth-based reference time when relativistic effects are included. In addition, ongoing corrections are applied to account for small variations in orbit and gravitational influences. Without these corrections, GPS would drift out of accuracy very quickly. The fact that your phone can guide you to a specific building demonstrates that relativity is not just abstract theory. It is practical, measurable, and essential. The importance of timing in GPS cannot be overstated. The entire system depends on synchronized atomic clocks. Even nanosecond differences matter. Atomic clocks use the natural oscillations of atoms, often cesium or rubidium, to maintain extraordinary precision. These clocks are among the most accurate devices ever built. Each satellite broadcasts its time signal continuously. The receiver compares the arrival times from different satellites. Because radio signals travel at the speed of light, the difference in arrival time translates directly into differences in distance. However, several additional relativistic effects also influence GPS. Earth's rotation introduces a phenomenon known as the Sagnac effect. Because the planet rotates beneath the satellites, signal paths must be adjusted to account for this motion. Engineers include these corrections in positioning algorithms. Gravitational variations across Earth's surface also produce tiny time differences. Mountains, ocean depths, and density variations slightly alter local gravitational strength. Although these effects are small, precision applications such as geodesy and scientific research must consider them. The success of GPS provides one of the most practical confirmations of general relativity. When Einstein published his equations in 1915, he could not have imagined satellite navigation systems. His work aimed to describe gravity as curvature of spacetime. Massive objects like Earth bend spacetime around them. Objects moving through this curved spacetime follow paths we interpret as gravitational attraction. In general relativity, time itself flows differently depending on gravitational potential. Clocks closer to a massive object tick more slowly. This phenomenon is known as gravitational time dilation. GPS satellites, being farther from Earth's center, experience less curvature and therefore faster ticking clocks. Special relativity introduces velocity-based time dilation. According to Einstein's equations, the faster an object moves, the more slowly time passes for it relative to a stationary observer. The satellite's orbital speed produces this slowing effect. The combined impact of gravitational and velocity-based time dilation must be accounted for continuously. Engineers working on GPS design explicitly include Einstein's equations in system calculations. Other global navigation satellite systems operate on similar principles. The Russian GLONASS system, the European Galileo system, and China's Beidou system all require relativistic corrections. Modern civilization relies heavily on this physics. Beyond navigation, GPS timing supports financial systems, telecommunications, power grid synchronization, and scientific research. Banks timestamp transactions using GPS synchronized clocks. Cell towers coordinate signals using precise timing. Electrical grids monitor phase alignment with microsecond precision. Relativity therefore underpins much of modern infrastructure. The story of GPS also illustrates the interplay between theory and engineering. Einstein developed relativity through mathematical reasoning and thought experiments about light and motion. Decades later, engineers designing satellite navigation discovered that ignoring relativity produced unacceptable errors. Theory and application merged seamlessly. Some early engineers initially questioned whether relativistic corrections were necessary. Practical tests quickly showed that predictions matched Einstein's calculations precisely. The corrections were not optional refinements. They were essential for functionality. Experimental verification of relativity extends beyond GPS. Particle accelerators observe time dilation in fast-moving particles. Atomic clocks flown on airplanes show measurable differences compared to ground clocks. Observations of light bending near massive objects confirm general relativity's predictions. GPS joins these as a daily, real-world demonstration. Understanding GPS also deepens appreciation of how interconnected science is. Orbital mechanics, electromagnetism, atomic physics, relativity and signal processing all combine to create reliable positioning. Removing any one element would disrupt the system. As technology advances, new experiments aim to test relativity with even greater precision. Improved atomic clocks may detect subtle deviations from current predictions. Space missions compare clocks in different gravitational environments to refine models. Future navigation systems may integrate quantum communication or even more accurate timing references. Yet relativity will remain foundational because it describes how space-time behaves under gravity and motion. The idea that time is not absolute challenges everyday intuition. In daily life, seconds appear constant and universal. GPS reveals that time depends on location and motion. Two clocks can tick at different rates depending on gravitational field strength and speed. This realization reshapes philosophical perspectives as well. Space and time are not separate backdrops, but dynamic components of reality. They respond to mass, energy, and movement. Navigation systems, which seem purely technological, rest upon this deep structure of the universe. Even small devices in our pockets rely on satellites thousands of kilometers away, moving at tremendous speeds, governed by relativistic physics. Each time a map application recalculates your route, it quietly depends on Einstein's equations. The reliability of GPS also demonstrates the predictive power of physics. Relativity was once considered abstract and counterintuitive. Today, it functions as a design requirement. The universe behaves according to these principles, whether or not we intuitively grasp them. As humanity expands exploration, precise navigation will remain essential. Spacecraft traveling to other planets must account for relativistic timing effects when communicating across vast distances. Interplanetary navigation will depend even more strongly on accurate spacetime models. GPS stands as a powerful example of how fundamental science transforms society. A theory developed to explain the motion of light and gravity now guides airplanes, ships, vehicles, and hikers worldwide. The connection between cosmic-scale physics and everyday technology highlights the unity of scientific knowledge. The next time your device shows your location instantly, consider the invisible corrections applied to each satellite clock. Consider that time itself bends slightly due to gravity and motion. Consider that a century-old theory remains vital to 21st century technology. Relativity is not merely a chapter in textbooks. It operates continuously above our heads in orbiting satellites. It keeps maps accurate, deliveries on schedule, and networks synchronized. This is Mattermosaic, piecing together the universe, one discovery at a time. If discovering how GPS depends on relativity changed how you see everyday technology, share it with someone fascinated by hidden physics. Tell us what scientific mystery you want explored next, and subscribe for more weekly journeys through the fabric of reality.